I'm going live.
Oh,
Looking good.
yeah, we're live.
All right, let's wait a little bit, then we can start. All right, hello and welcome everyone to today's brand new episode of Quadcast. I am your host, Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, ask us questions during the episode, and we'll get to them. So without further ado, let's get to it, Tim. So Tim, this is an interesting discussion, mostly around the notion of cause and effect. And this is something we're all intuitively aware of as humans on this earth, in which I like, let's say I push a glass and I move it and it moves over. I can say, in everyday language that I caused this to move over. So I guess want to examine this more on a physics basis. Like, is this actually a real thing? Or is it, where does it lie in the scope of things? So I guess, Tim, can we start with a loose, the classical high level definition of what is cause and effect, or causality, as we'll refer to it in this episode?
Yeah, I think one thing to keep in mind is that there is a difference between what physicists call causality and what most people call causality, and I think it's important to distinguish the two. And I think in this episode, we will refer to causality in the most colloquial way, the way that most people understand them. And it's this sort of very intuitive notion of cause and effect. It's this idea that, you do something and something else happens. And if you hadn't done that thing, chances are that what have happened wouldn't have happened. There's sort of this, cosmological purpose and ordering of events that happens one sequence after another. I think that's, it's not a rigorous definition, but I think that's a fairly intuitive way to define it. And throughout this episode, I think we'll see that this notion of causality as we know it actually does not exist in fundamental physics, even in just classical physics, quantum physics, relativity. We have a much more technical definition of causality, but it almost seems nothing like the ones that we view as causality. And as it turns out, at the end of the day, we'll see that this definition that we have actually has a lot of human bias into it, and we'll explore deeper reasons why.
Yeah, absolutely. I mean, that's a good sort of crux of the episode. Now, so what, to start off with, let's talk about when I learned in classical physics, for instance, when I throw a ball and it hits another ball and causes that ball to move and change its momentum and move in the direction that I tossed the ball in. Can't I say that that ball caused the ball I threw caused the other ball to move forward? Or is that ambiguous? It seems fairly, straightforward to me, but can you break that example down a bit more?
Right, yeah. And even if you ignore all the complications of contemporary modern physics, even this very basic example is actually a little ambiguous. The crux is there's Newton's law. And Newton's law tells you that every action has a reaction. So, for example, if you push a ball, causing it to move, you might feel like you have agency. It's because I decided to move the ball. That's why I moved. But remember, Newton tells you that, well, as much as you push the ball also pushes back. So in a very real way, if you take that law, kind of think about that a little bit, in a very real way, the ball is also pushing back to you. So are you pushing the ball, or is the ball pushing back to you? Already there's an ambiguity right there that arises.
Huh. Then I guess that makes sense to me. But then if we look at other examples, like say usually in the field of causality, I see a lot of examples involving like medicine, for example. Let's say you have a headache and I give you an aspirin and you take that aspirin and then it's like, oh, your headache is gone. And I do this, I do this across many people who I believe are similar enough to you. And let's say I give half of them no aspirin, half of them aspirin, and it takes away their headache. I can then say that, oh, this like there's a cause and effect here. So I wanted to ask you, like, in that example, is there ambiguity?
Yeah, and I would say in that example, there actually is a lot of ambiguity.
Hmm.
And even though we call these cause and effects, if you look at the physics in greater details, these are actually very different processes. If you compare like the medicine example to like me pushing a ball,
Mhm.
like me pushing a ball is a very direct, I just push the ball, there's some interaction going on, even though there are a lot of molecules going, happening. I push the ball, it happens, right? But if you look at, let's say you take a aspirin, the chemicals goes into your body, it dissolves, and then ultimately at the cellular level, the proteins or whatever, I'm not familiar with the biochemistry of this, right? It might inhibit some proteins, and all of the little interactions ultimately will still follow Newton's law, right? Every medicine that binds to a molecule will also have a reaction. But then but then when you add up all these complicated steps, and then you look at the beginning and the end, it's almost like there's a new like if you look at the atomic level interactions, it's really hard to see what's causing what. It just happens, right? But at the end of the day, you see that, hey, I took a pill, I feel better. That notion kind of emerges out of these little interactions. So I would say that kind of causality has more to do with sort of emergent phenomenon. It's not easily broken down into atomic interactions that happened.
Yeah. Can you also, I guess, like comment on how causality or this cause and effect notion is more of a statistical notion in the example I gave? Like, why would it be difficult to establish causality for a single individual? I just want the audience to appreciate that more so.
Yeah, and the issue is that the world is filled with noises, basically. The vast majority of things happening in the world are noises that are completely out of our control. Like even in this room, there is noises from the air, noises from the light, from the sun coming in, and even noises from, I don't know, dark matter particles, neutrinos streaming in, or just remnants of the primordial universe, right? These noises are just quantum field fluctuations even, right? These noises are completely irreducible, right? And as a result, when we talk about an individual instance, let's say I don't know, my finger feel, let's say I feel some sensation in my finger. How can you attribute this to? Is it because the air molecules is hitting my hand? Is it because my neurons misfired? Or maybe like a neutrino knock off one of the DNA molecules or something. You can't be, because the noise is so uncontrolled, it's just impossible to find out. And as a result, we built statistical apparatus, which is just an approximation of the real world, to kind of ignore all these noise, because these noise the humans cannot control. So so we'll go crazy if we try to measure them and quantify them in more details. The society would just go crazy. You just can't do that.
Yeah, that also makes sense, in which you're saying that there are a lot of, especially in more kind of emergent phenomenon like us as human bodies with lots of interacting pieces, or rather complex systems with lots of interacting pieces, it becomes really hard to say like what caused what. And there's of course like noise and how these things interact with themselves and the environment. So it just becomes a giant jumbled mess. One thing I wanted to ask about that you mentioned is this notion of like time ordering. So this notion of like, when I see something like me pushing a ball, I can say my hand moved first, then touched the ball, and then the ball moved. So I can give a loose notion of causality to that, or cause and effect. My question for you is, like, in physics, can we describe the notion of causality with this time ordering of, like, saying, oh, this event preceded this other event, so we could say that this event maybe statistically caused this other event. Just want to get your thoughts on that.
Yeah, certainly the time ordering is part of that. We know that we can't go back in time. Like I
Mhm.
can't go back in time and correct my mistake. So for sure, part of that intuition is that things in the past cause things in the future. You know, but that notion gets murky. We can go into that in more details because there's Einstein's theory of relativity that tells you that space and time is relative. They're not absolute. So the ordering is actually not absolute. But let's ignore that for now. Let's say we're all on Earth, and you look at uh, the time ordering of events. But if you try to define causality this way, that's kind of as far as you get. You just get this general idea that things in the past cause things in the future.
Mhm.
But that's not very useful, I think. Like for example, like imagine there's a presidential election. Let's say a president gets elected.
Mhm.
Would we don't tend to say that everything that happened in the past caused the election. I mean, sure, you can say that, but that's not very informative. We usually come down to the fact that, oh, this person get X number of votes versus Y number of votes. That's why he or she gets elected.
Mhm.
But we don't think about the air molecules in Panama, right?
Mhm.
But that could have had an effect. You know, the air molecules in Panama could have caused a hurricane that causes rain in a state in New York, and I don't know, mess up the election votes, right? So I would say just time ordering alone is not enough.
That interesting point. It seems like you've sprinkled hints of our friend chaos theory. So can you explain this? And I believe what you're referring to is the, like, effectively the butterfly effect. So can you describe chaos theory, how it pertains to this, and like the butterfly effect, and also how it pertains to this as well, this discussion?
Yeah. So basically, why does that matter? Is because, like you said, if we try to use physics to define causality, sort of the best we can do is this ordering of events. But the
Mhm.
ordering of events becomes too large. The only thing you can say is the past caused the future. So that's pretty useless. So
Mhm.
we need some ways to separate, you know, different sort of I I don't like to use the word cause and effect, but like
Mhm.
imagine cause and effect exist, then we need some ways to separate them. And the thing is, in physics, why does noise matter? Noise matter because of this butterfly effect, because the world is chaotic. What that means is that even a tiny little bit of noise, if you can't take it into account perfectly, just that little change can make the system completely dramatically different. And that this kind of adds a layer of unpredictability, and because of that, it murkies up cause and effect. And
Mhm.
so so if you ask the question, hey, look, how do I get a better understanding of cause and effect? You have to take this kind of dramatic effect into account.
Yeah. I'd also like to mention a story for the audience that I think that'll help shed more light on what you're saying. So there was this weather scientist named Lorenz, or I think maybe a physicist. I'm not sure what his profession was, but he was essentially trying to simulate weather, or trying to predict weather. And he had these set of equations that are called the Lorentz equations. I won't get into exactly what they are. And and this is the time when they were using, I think, computers the size of, like, large rooms and whatnot. So he would basically have these equations that would simulate what the weather would be, at each time step. And he basically stopped it at a certain point, And then the next day he changed the numbers by a little bit, didn't think they were that much. And then when he came back again, he found out that the results diverged by a lot, like just immensely, like a completely different system in some sense, or different state for the system. So, Tim, that's what you're referring to, is that any small changes in initial conditions, given, a certain amount of time, will just completely diverge from like other initial conditions that are very close to them. Is that what you're trying to say?
Yeah, exactly. Yeah, it's this idea that noise, however small, can cause dramatic differences in a system, and that's very unfortunate because when we talk about cause and effect, you might say, oh, let's just ignore the noise. Who cares whether an ant was crawling on the ground or not? Who cares about that, right? We're talking about presidential election. Why do we care about that? But it turns out that all those things actually add up to be pretty damn important. So, but then what is the solution? Well, it turns out that we just have to ignore them because there's nothing else to do.
Yeah, so that comes back to our round robin to our discussion about like that this is essentially a statistical kind of notion, right?
Yeah, exactly. So we use statistics to approximate what that looks like. So like and for example, like let's say you take a drug and I don't know, let's say it's a treatment for cancer or whatever, right?
Mm.
And maybe the doctor tells you that, hey, there's like a 60-40 chance of working. And what the doctor means is that, in our study, that just is the number, because there are things that they can't control, things that could have dramatic effect that they just could not take into account. And when they average that out, if you look at people who are similar to you, they have, I don't know, 60% survival rate or something like that, right? But yeah.
Oh, go ahead. Sorry.
Yeah, but keep in mind that statistics is just an approximation of reality. It is not reality itself. That's the key here.
So actually, I want to ask you a kind of impossible thought experiment for the moment. Say classical physics is the end all be all, like there's no quantum mechanics whatsoever. It's all classical. And let's say you had computers that could compute things to infinite precision, and you had the exact law of physics. Could you still establish cause and effect, or even with that, you still couldn't?
I would say probably still not, and because just running the computation itself would cause changes in the system. So I don't know. It's kind of goes in a loop a little bit, right? Because the computer is part of the system. You can't.
Yeah.
Yeah. So I'm not sure how to think about that. Like, how can you simulate itself? Like, you can't have a computer that simulates the effects of the computer itself, right? So you can never perfectly control all the noises. So yeah. So even ignore quantum physics. I think that's a no-go, I think.
Okay. And is there any, I guess, intuition behind how these noises like add up and make completely different like change the system in a completely different direction? Like it seems kind of I don't know, when people may first hear about this, like, oh, the butterfly effect, like a flap of the so-called butterfly, proverbial butterfly, makes a hurricane come in like 2 years. There's actually a different reason why it's called butterfly effect, but that's a story that people typically go with. So is there any like intuition behind that? Like it didn't have to be that way, but like is there something that of like why that arises?
Yeah, I think I don't think there's an intuition on why it has to happen that way. It has more to do with why not. Because let's say we humans like to see a rainy day, right? But nature doesn't care about that. The air molecules has no business into making it a rainy day for you. So nature basically does not care about the way we categorize systems, or we separate rainy versus not rainy day, right? But nature doesn't really care for that. So that's why nature really likes to scramble things around. So there's this saying, Murphy's Law, right? Whatever is possible will tend to happen. And that's what nature does. And so that's why even though you say, oh, but like, for example, oh, maybe my wedding isn't tomorrow, I really would love it to not rain.
Mhm.
It's impossible for it to rain because it would be terrible. Well, sorry, but nature is going to try, right? If it has a way to do it, it will do it. So it will try to mix things up for you to keep things interesting to some extent. So it's really nature's ability to mix things up to test out all the possibility that give you this dramatic effect.
Yeah, yeah. That makes sense. So let's talk about quantum mechanics. We haven't really, so far our discussion's been entirely classical and as if quantum mechanics doesn't really exist. But now I'd like to bring it in. So how does causality and quantum mechanics play in based on all the things we've discussed, like time ordering, statistics, throw the whole sink at you with that question?
Yeah, I think with classical physics, people still have this hope that maybe there is kind of a notion of causality, you can say. Oh, like the ball moves first and then something else moves later. Maybe we just try really hard. We can define causality in a better way. There was still kind of this lingering hope.
Mhm.
With quantum physics, all hope goes away. I think that's the problem because
Okay.
every calculation in quantum physics has to do with probability.
Mhm.
Certainty completely goes out of the window. And also, this probability is probably still an approximation to what happens. And in quantum physics, it tells you that everything fundamentally is unpredictable. So if that's the case, let's say, I don't know, I feel a pain in my finger. Well, I could have not felt it. Like how would I even know what caused it, right? There are all these factors that changes the possibility of something. It's
Mhm.
almost like this it's almost like a glitch in nature, right? There's plausible deniability for everybody because there is possibility for it to go the other way. So it
Mhm.
just completely destroys almost any plausible notion of causality.
Mhm. I guess like one question I have is, isn't that similar to even classically? Because you mentioned there are all these like different factors that play in and we can't possibly predict all the effects that the environment has and whatnot. So we make this statistical approximation to begin with and say, oh, there's like some amount of ignorance we have that's captured by the noise. We're going to throw that out. Can't you apply the same thing in quantum mechanics, or why is that even more challenging? Or if not, just you just can't do it.
Well, I mean, if you like the idea of statistics, yeah, you can argue that's more straightforward, right? So I mean, I wouldn't say it's more complicated. It's just the entire philosophy is different. In classical physics, you can look at the trajectory of a ball moving,
Mhm.
and it almost feels like the ball is filled with purpose, right? It goes from one location to another.
Mhm.
And now in quantum physics, the entire calculation is different. The only thing you can calculate is what's the chance I can find a ball there. You can't
Mhm.
even really talk about what how the ball is moving. I mean, you can approximately talk about it, right? But it's just the entire philosophy is different.
Mhm. So so I guess like one question that I have is so yeah, so we approximate quantum mechanics with probabilities, as you're saying, and I also believe this as well, that probabilities may not actually be the thing that like is truly happening, is just more of an approximation. But let's roll with probabilities for now. So let's say like I have like a particle like in a box, and I throw some light at it. I measure it in this like region of space. I can't measure it like infinitely precisely due to Heisenberg's uncertainty principle, plus other things that we've talked about in past episodes. You can't localize things to points. But besides that, I localize it to a region. And then later, like maybe some very short amount of time later, I throw like another light particle at it or interact with in some way, and I say, oh, it's like most likely here. So, still in the same kind of region. So can I say that like me measuring it once and then me measuring again caused it to be in that area? Most likely. I mean, of course, it could like bounce off and be at the other end of the box. Like I'm not discounting that, but most likely it's going to be like in that spot. Yeah.
I mean, you can do a calculation, and the calculation might show you that the ball might stay in the same place, but the calculation does not tell you why, basically. If like so what you could compute is you can say, hey, so you can try two different scenario. Let's say I poke the ball and then I find the ball in the box, and I don't poke the ball and find the ball in the box, and then I look at the different probabilities, right? Then what we can calculate is what we call like a cross correlator, like the difference, like the difference. It's almost like a control experiment. It's like taking a drug. Like imagine you take the drug, and then you say, hey, do I get a headache? Versus you don't take the drug, well, do I still get a headache? You can do that in quantum physics. Like you poke the ball, is the ball there? You don't poke the ball, is the ball there? That is the closest thing you can do to like cause and effect. But at the end of the day, you're still gonna just get some number.
So are you saying that the only thing we can really measure, use measure in quotes, measures correlations more than like cause and effect?
Absolutely, yeah. It turns out that if you open any quantum physics textbooks, the only things you find is just a bunch of correlations.
So I guess then so correlation, we know from statistics literature of like how how one thing follows another thing, or how they influence each other, and that also appears in quantum mechanics. But I thought there's usually there's a way classically to go from correlation, saying, oh, these things are correlated, to forming some kind of model and saying that, oh, one thing caused another thing. But what you're saying with quantum mechanics is there's no notion of cause, because you don't have an explanation of why you measured it to be a particular value, even based on past measurements. Is that correct?
Yep, absolutely, yeah. And to make matters worse, one could argue that, hey, doesn't statistics kind of have a well-defined, if you like data science, you can say, well, doesn't data science give you a good definition of causality? You can do a control experiment, blah blah blah. Look at these probability, and then you can say, hey, look, if I take a pill, look at if I get headache. If I don't take a pill, look at my headache. There's a difference in the amount of headache I get probabilistically. So what gives? Well, the problem is, what is probability? It's an approximation to real life, right? It's telling you that, hey, if you take 100 of the same people in the same condition and give them pills versus give them not pills, you get this outcome, right? But sorry, quantum physics says that you can't do that. There's no cloning theorem, no deleting theorem, and a bunch of other theorem. And because quantum information is conserved, we talked about that in previous episode, it means that you can never 100% replicate any experiment. It's just not possible. So it tells you that, hey, gee, statistic is just an approximation, but you can't take it too literally. And that's why, in quantum physics, it's even murkier. Even though you do calculate correlators, the statistics though is it's emergent, I would say. It's not the fundamental bits.
So okay, so that to me makes sense. Can we talk about briefly touch upon time ordering? Does time ordering make sense in quantum mechanics, or is that itself also ambiguous?
Yeah, so that's a really interesting thought. And I think that we actually have to go to Einstein, because the ordering of time has to do with space-time, right? So we have to go to Einstein's theory. And it turns out that Einstein's theory and quantum physics actually works really well in that regard. So even though time is not absolute, Einstein's theory forbids you to go back in time to murder your grandpa. It forbids you from doing that. So even though space and time are not absolute, it turns out that the ordering of what happens first after another is consistent as long as as long as things are not too far away. And this is what we call causally connected. As long as things are not too far away, let's say we're on Earth, then the time ordering of events makes sense. So you could kind of calculate these what I call the control you could run control experiments, right? Because that's one of the prerequisites. If the result happens before you administer the pill, well, that's not a control experiment anymore. So that's a prerequisite to have a consistent notion of time ordering.
I see. Wait, so okay, so when you talk about things being like causally connected, you mean that basically you and I can send like particles of light to, or maybe particles that move at the speed of light and interact with each other, versus like if we were at such, we're moving away from each other, or we were such a distance away where, if I sent you a light signal, and I measured a certain amount of time and it hasn't reached you, then I can say we're not causally connected in that span of time. Is that fair to say?
Yeah, exactly. So yeah, and this is the reason why when I tell people about Star Wars, I keep throwing like the idea of intergalactic war does not make sense because the notion of causality doesn't make sense for things that are very far away. So like you can kind of imagine what's going on in our neighborhood galaxy, Andromeda, or actually even within our own galaxy, right? Maybe there's like an alien Sahil, doing a podcast over there, right? But then depending on who you are, if let's say you're traveling in a spaceship, you pass through Andromeda and come by Earth. To you might see the alien Sahil give the podcast episode first, and then we do our episode. But then another person riding on a spaceship might see us go online first, and then the alien goes online. So the ordering of these episodes might be different if we're really far away. So that's kind of the conundrum here. That means that you can't do control experiments that far away.
So you're saying because, but that I could still shine a flashlight, at a really powerful flashlight at Andromeda, and after some amount of time, they'll see me flashing that light. So, what does it mean in this context to be like out of like not to be causally linked to each other, or out of the causal sphere of influence, as Mikey talks about? Yeah, how does that play in? Because given enough time, I can reach you with my light signal. It just takes a certain amount of time. It's not instantaneous. So I just want to understand, like, why is the ordering of events different, even though I could, reach you after a certain amount of time, and then we're like connected?
Yeah.
Wise.
Yeah, let me be more precise, and I'm talking about like a third observer, because in Einstein's theory, there's no absolute notion of time, so you always have to specify an observer, right? So if you have a third spaceship, from their perspective, the ordering could change. Of course, if you are able to send a signal to Andromeda, eventually they catch up. Once they receive that signal, those events become causally connected. And in fact, we receive light from Andromeda. We can, if we have a telescope powerful enough, we could observe maybe an episode happening on Andromeda, and to all the people on Earth, we would agree, hey, look, I don't know, these guys have the episode first. We are copycats, right? Maybe. So we will agree on Earth what's going on, but we're not going to agree with necessarily the aliens, I don't know, in Andromeda. It doesn't even make sense to talk about the aliens on Andromeda, because when we're disconnected, there's no way to communicate each other with one another. Only until, I don't know, we send a signal back and then we compare data, then maybe we can reconcile. But
okay. So are you saying, like, let's say us on Earth are doing this podcast episode right now, and let's say on Andromeda, alien versions of ourselves are also doing a podcast. and then we like each, get into our spaceship and meet each other midway, can we then decide on a time ordering, or how does that work?
Um, I have to think about that a little bit. I think
Okay.
it gets pretty damn convoluted. But
Okay. Okay.
when the two people meet up, yeah,
Yeah, we can yeah, we can punt on this for now, and we can come back to this later. Yeah, so okay, so I just wanted to talk about time ordering because that's essential for
mhm.
the notion of causality, that you need like a time ordering. But even okay, so now let's take a step back, and we've gone from classical physics to chaos theory, and then to quantum mechanics, and we're basically now coming to the conclusion that we stated at the beginning of the episode, that causality itself is bunk. It's not. It's essentially an illusion. Doesn't really exist. Now we've talked about this like galactically at very small scales, but I want to understand from like a human experience standpoint, like what does this mean? Should we just like give up, like, because is there no true causality? Like, why bother having it, would be my question to you. And let's say in science, why do we even seek causality?
Yeah, and I would say it's a matter of practicality. Like even like there are many concepts in physics, even though it's not totally concrete, it is useful. I think one of the powers of causality is it helps us gain control of the world, right? Like I mean, some of the philosopher mentioned these. Like I think David Hume or whatever, he was saying that, oh, the sun comes up every day and goes down every day, but how do you know that it always does that? We always think that it's going to happen. Take it as truth. But what if one day the sun just goes poof, right?
Mhm.
But you can't prove that it wasn't going to happen. But
Mhm.
it's very useful observation that the sun comes up every day and goes down every day. You
Mhm.
know, sure, you can't absolutely prove it. And of course, I mean, with physics, you can kind of sort of guarantee that it doesn't go poof if you ignore maybe quantum fluctuation, catastrophic events in the cosmos that you can't control, right? But I think at the end of the day, it is that from these observations, we can hone in on the correlated. We hone in on the factors that we can control and see how, when we control those factors, how the world responds. And that helps us do science and live on Earth. I think that's why, even though these notion of causality is not well defined, like these are knowledge that help us navigate the world, and therefore they are useful.
Mhm. So you're saying essentially it's a reliable, I mean, robust and reliable to a certain degree of approximation.
Yeah, exactly. Like for example, like we can debate all day long whether a butterfly um, affected the presidential election. We can debate
Mhm.
all day long, right? But we can't control all the butterflies on Earth. Like even if we get down to the nitty gritties of, oh, how a butterfly flapped its wings and that caused a hurricane, I don't know, in New York or whatever, and then that messed up the presidential vote. Well, there's nothing we can do about it.
Mhm.
Like you're better off spending your effort trying to convince voter to vote one way over another. Those are more persistent. So I think
Mhm.
when we systematically remove the noise, like the butterfly effects or the quantum mechanical noise, or things we don't control, we end up with things that we have agency over, like taking drugs, pushing the ball around, I don't know, driving to get grocery. These are things we can control. And that help us navigate the world.
Yeah, that's interesting. I guess like one last question on my side, before we call it, is so in the context of like physics experiments, like say classical physics experiments like time of Newton and stuff like that, there's the world's chaotic, at least classically speaking, yet like people are able to do these experiments and ignore a lot of the noise. And why is it that that's actually reliable? Like it didn't produce vastly different results, or were the systems so simple that you could do that, or like, yeah, I just want to understand that more.
I think part of it is by design, because if an experiment has so much noise, well, that's a terrible experiment. So we have to design experiments that isolate certain salient features of nature and kind of, I don't know, like amplify it in some ways, right? So and there's lots of instruments that help us do that amplifies quantum mechanical signal into classical realm, so that we can see them, right? And I think another part is also because of luck. And what I mean by that is that our universe didn't have to be like that. Our universe could have been I don't know, like a completely featureless soup of plasma with nothing that's interesting. And the only noise, the only thing that exists is just thermal noise. The only thing that interesting that you see might be butterfly effects. I mean, just look at the sun, right? There's solar storms coming out, blasting out. And there are a lot of features on the sun, but they are so, what's the good word? Chaotic and destructive. That like you can't possibly do very much with it. It's completely out of control, more or less. So basically, we're lucky enough to live on Earth with a temperature that's not too high, with structures that have hierarchies, so that humans have arms and legs, have objects like rocks and tables to play with, and we're able to manipulate the world that way. And that turns out to be not obvious. Not all universes are like that. And it's the best explanation right now. I think it's anthropic. It's just because.
Yeah, I would say I would agree with you on that. So we're almost at time. So I wanted, in tradition of all our episodes, I want to give you a chance to leave the audience with any words of wisdom that you've learned upon meditating that causality is just an illusion.
Yeah, well, first of all, I want to clarify that to my physics friends that causality is not an illusion, because in physics we legitimately have a definition of causality, but it's nothing like the causality that we experience, right? So I would say, well, the causality that we experience is an illusion.
Okay.
And like always, I think the physics lesson is that our universe once again humbles us. Like what we thought is so important and sacred, like the more modern physics we learn, the deeper we dig, it turns out that, because this idea of cause and effect, it feels like a human insistence, basically. But then again, nature gifted it to us that we're able to do that. So it humbles us, and also I guess be thankful that we have causality to play with, because otherwise it would be a pretty dark world, I would say.
Wait, what is the physics definition of causality again? Can you remind me about that?
Oh, yeah, the physics definition is not so much of a definition. It's basically like a requirement for theory. And I'll tell you technically what it is, and you be the judge whether it has anything to do with our notion of causality. The technical definition is that a theory is causally sound, a fully quantum and relativistic theory, if their out of time cross correlator is zero outside of light cones. That's it.
Oh yes. Yeah. That yes. I've seen that. Especially in one quantum field theory textbook, I think by Peskin and Schroeder. I forget why they use that, but they make some kind of argument. Yeah, that I would agree with that.
Yeah. So it has nothing to do with, well, it has very little tangential relation to our everyday experience.
Yeah, I think I'll sum it up okay, let me try to sum it up to the audience and let me know if you think that this is the correct way. I think in a nutshell, what you're saying is that things that are outside of being causally communicated have you can't really agree on the time ordering, and you can't they don't really interact with each other if they're outside the causal sphere of influence. Is that fair to say?
Sort of. I would put it that way, that things that are too far away, you cannot do control experiments, and that's why there's no notion of causality, even statistically. So causality is done through control experiment. That's the best you're gonna get with statistics.
Yeah, that's totally fair. Well, so yeah, thank you for humoring me on that. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thank you all. See you guys. Bye.